Good morning. I'm going to kick us off right away at 11, though anticipate attendees to continue to trickle in here. But I will start with welcoming you all to this Conservation Applied Research and Development webinar today on industrial electrification through heat pump adoption for process loads. We're really looking forward to the presenters presenting and so happy to have all you attend. I'd like to cover a few housekeeping items before we start. All attendees will be in listen-only mode. We will answer questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipse in the lower right of your screen as indicated on this slide. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be made available on the department's website. The slide set from this webinar will be emailed to all registrants within 2 weeks from today's broadcast, as well as also will be made available on the website. And finally, if you'd like this closed captions on the webinar, click the CC bubble in the lower left of your screen. I am Lindsay Anderson, the Eco Research Director at the Department of Commerce within the Division of Energy Resources. Here, I identify and analyze gaps within utility energy conservation and optimization programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. With me today is Adam Zoet, who is the Eco Regulatory Analysis Director within the Eco Business Unit at the department. Adam's work includes leading the evaluation of ECO's cost-effectiveness methodologies, formulating regulatory policy guidance and analysis frameworks, and assessing Minnesota utility energy efficiency programs. He's the project manager from the department on the research that is the subject of the webinar and will help moderate and facilitate responding to the questions during today's presentation. Our presenters today are Dave Bohack, Shonda Biddle, and John Flanagan from Center for Energy and Environment, as well as Shandon Rao and Akila Rao from Graphite Data Mining. Dave Bohack is the project manager and a senior research engineer at CEE. There, he has managed building envelope and HVAC emerging tech field research and market studies. Shandon Rao is the president of Graphite Data Mining, where he facilitates a data-driven energy management strategy for several large customers in the manufacturing and commercial sectors for continuous improvement and sustainability. Shonda Biddle is the director of large commercial and industrial market solutions at CEE. She leads CEE's ideation process to vet and develop commercial and industrial programs. John Flanagan is an energy engineer at CEE, where he performs commercial energy audits and supports research and consulting efforts. Nikila Rao is the general manager at Graphite Data Mining, where she serves as a liaison between utility program stakeholders and customers enrolled in these programs to drive program objectives. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund. CARD was established in the Next Generation Energy Act of 2007. Research areas were expanded within the passage of Minnesota's 2021 Energy Conservation and Optimization Act. The purpose of CARD is to fund and help Minnesota utilities achieve their energy savings goals through the funded research. $2.6 million is set aside annually for the CARD program, which awards research grants and a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their energy conservation and optimization portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is within the industrial sector, and our presenters will share results from a recent CARD project to identify industrial processes that are the best candidates for electrification using high temperature heat pumps instead of direct heating with natural gas for the creation of process heat in small and mid-sized industrial facilities, and working on developing insights to support utility conservation program implementation. With that, I'll turn it over to Dave to get into the main portion of today's presentation.
Well, thanks for that introduction. As Lindsay indicated, we are presenting the results of a CARD research grant market study on the potential for heat pumps for industrial process loads for Minnesota plants. All of our team is presenting information, so we will be doing a little bit of a tag team. Next slide, please. For today's presentation, we will first provide background information regarding the project justification and goals. We will then describe the types of heat pumps that are available for industrial applications and the best industrial application for heat pumps. For that, we primarily relied on published reports, but we also conducted stakeholder interviews to get information from plant managers, heat pump manufacturers, and designers relevant to Minnesota applications. This project also included surveys of 6 Minnesota industrial plants to identify heat pump opportunities, and we conducted a high-level evaluation of the best opportunities. That additional information provided the basis for an evaluation of the market potential for gas savings for Minnesota industrial facilities. And then finally, we've generated a high-level roadmap for market adoption for industrial heat pumps. And we will wrap up the presentation with our overall conclusions. Next slide. So I'll get things started by reviewing the justification for this project and the goals. Next slide. Industrial heat pumps development started in the 1980s. The systems have great potential to decarbonize industrial thermal processes, but they haven't seen extensive use in the US. For example, the 2018 Minnesota Energy Efficiency Potential Study found that the industrial sector had the second highest potential for natural gas savings. One of the largest opportunities in the sector is process heating, which is 13% of all industrial potential savings. Fortunately, Europe is ahead of the US on the use of heat pumps. There are now industrial heat pumps that can provide 120 to 400 degree temperatures and can use waste heat to improve efficiencies. Previous market studies have identified a few key processes where industrial heat pumps can be applied. Those include processes present in Minnesota facilities, including food processing, brewing, corn milling, and paper and pulp processing. Next slide. So the project goals we developed to address the needs for greater market adoption. As I described previously, this project was intended to do a deeper dive into the industrial heating processes present in Minnesota that best lend themselves to heat pump applications and identify equipment available for those systems. We recruited a stakeholder working group to get feedback on opportunities and formed a utility advisory group to provide feedback on our findings. We also wanted to use our industrial plant site surveys to evaluate industrial heat pump opportunities for actual processes and see if those could lead to possible demonstration sites. Finally, we identified tools in the process for high-level screening and designing heat pump applications. We also used experience from the heat pump evaluations at the 6 sites to confirm the technical potential for the systems. And then we developed a roadmap for activities needed to improve market adoption. Next slide, please. And with that introduction, I'm going to pass the presenter's role to Nikila, who will discuss the results of our stakeholder interviews.
Thanks, Dave. So stakeholder interviews were conducted to gather diverse feedback on the market potential for industrial heat pumps, as well as to identify facilities that could serve as a demonstration site for this technology. Next slide, please. Representatives from 4 stakeholder categories included those listed on this table. They were plant managers, subject matter experts in industrial design engineering and energy consulting, IHP manufacturers representatives, and utility program staff who manage programs for industrial customers. We believe these categories typically influence market potential. Interviews focused on topics common to all stakeholders, such as familiarity with IHP and thermal processes applicable to heat pump systems, as well as other areas more relevant to a specific stakeholder category, as you can see in this table. Thank you. This table provides a summary of the diversity of representation and level of familiarity that the groups have about IHP technology. Most plant managers and utility program staff are familiar with heat pump systems and are actively building on this knowledge through webinars, conferences, and published content. Our survey showed that the other categories, that includes manufacturers, the consultants, and the design engineers, are very familiar with industrial heat pumps. However, we targeted individuals who were likely to be familiar with IHPs, so this should not be considered a representative sample. Next slide, please. Some key insights that emerged from the interviews are highlighted here. Overall, the feedback provided a reasonable understanding of barriers and opportunities for adoption of heat pumps. Further, the prevalence of sustainability goals is rising, and separate funding streams can reduce friction for projects targeted directly at energy or carbon savings versus production goals overall. This concludes my section. I'll hand off to the next presenter team, which is Chandon and John.
Thank you, Nikhila. If you go to the next slide, please. So to start with, just to set the stage, what is a heat pump? I want to say it's like your air conditioner at home. It takes heat from the room to cool it and then rejects it to a warmer temperature outside. And so heat pump is a key step in recycling waste heat, taking waste heat that is at a lower temperature and delivering it at a higher temperature that can be more useful for other applications. And there are applications in the industrial process that could benefit from it, thereby reducing greenhouse gases and associated with the greenhouse gases associated with using other fuels for heating. And the key to application of heat pump is really the 3 R's for waste reduction: reduce the demand, reduce high temperature heat, reuse the high temperature heat, recycle waste heat. And that recycle waste heat is the part where electrification and heat pumps comes into play. So if you go to the next slide, please. There are different types of equipment available for doing this, different types of cycles. And they're classified into two: closed cycles and open cycles. And you can see there's a lot of equipment that is available. And all of the equipment elements needed for a heat pump are proven technologies. However, most often this will need some custom configurations for industrial applications because it's not as cookie cutter as doing the air conditioning at home. And primarily we see two types: mechanical vapor compression, MVC, and mechanical vapor recompression being the common applications. Now, if we look at the process side and what are the best processes, this chart shows a recent study of industrial applications for heat pumps and the market potential for the applications. The green line shows the impact on the electric infrastructure. So the blue bars show how much of the boiler fuel gas could be supplied through heat pumps. And the green line shows how much the electric infrastructure might have to be increased in order to provide the electricity for the heat pump. And obviously, we want something that has a high blue bar and is low on the green line so that the investment cost could be lower. And there are processes in the food and beverage sector that show significant potential for application for heat pumps. And if you look at the first 9 bars from the left, they're all in the food sector. And what we also know from other DOE studies is that in the food sector, there are a lot of hot water applications, and about 90% of these hot water applications could be candidates for application of heat pumps. So how do we translate this to application in the Minnesota market? The best data we have happens to be the gas market data that was done by an MTAP study in 2010. And we were able to look at the average terms per plant by utilities and by sectors. And you can see that the green highlights show the segments with the highest terms average per year per plant. And the food sector is one of the sectors that could benefit significantly. And it matches what we saw in the findings in the CalNest Next report. So in Minnesota, the food sector was identified as one of the key sectors for understanding the potential for adoption of industrial heat pumps. I will now switch topics to the site surveys that we did and the evaluation of results to assess the potential at the sites. And I'll first go through the three-step appraisal process that we took. The first being the feasibility. We look at where we can pick up heat and where we can use it, making sure the pairings overlap in runtime and that temperature lifts are reasonable. Second is the suitability, that once we've identified a good pairing, the question isn't whether equipment exists, but rather which technology is the best fit. So this step becomes an optimization exercise. Finally, we consider the applicability, which looks at case-specific and organizational factors, such as utility incentives, rate negotiations, space, plant motivation, things of that nature. If the pairing is feasible, incentives are on the table, and leadership is committed, then it makes sense to move forward with a design-build proposal for heat pumps. So that's the methodology we took. Now, looking at the suitability, to begin suitability testing, normalized fuel cost, which would be the ratio between the electric and gas cost per unit energy, must be linked to a required break-even COP. COP, very simply, is a coefficient of performance that says for 1 unit of energy I put into the heat pump, how much units of heat do I get out? And higher the COP for a single unit, I get more heat out. Now, when we look at the gas and electric costs and the ratio of the gas and electric costs, you can see on this graph that depending on the electric costs and depending on whether demand charges will be impacted by the heat pump COP can be established based on prices in the site for the site. And here we can see that if demand is not included in the electric cost, a lower heat pump COP would be cost effective. Whereas if there are demand charges, we would need a higher heat pump COP. And the heat pump COP depends on the temperature lift to be achieved by the heat pumps and the type of heat pump and the fluids used. So I will now switch to the 6 sites that we selected for evaluating the potential for application of industrial heat pumps. Site participation in the study was initiated with an interview process to obtain current site awareness, sustainability goals, and business priorities. Several of the sites have had a positive experience leveraging utility programs to achieve energy efficiency. The key factors for success were the presence of corporate initiatives for energy efficiency, plant-level sponsorship, and experienced energy champions. We also found that sustainability was a key driver for 2 of the sites. When you look at this table, it gives you an idea of the physical size of the facility, energy consumption, type of processes, and then you can see the spark gap, which is the ratio of average electric cost to fuel cost. And these numbers range from 3.98 to 5.29, which means that the spark gap is 3.98 to 5.29, and for every unit of gas energy to get the same from electric, it would cost us 3.98 times more than gas, or 5.29 times more than gas. And therefore, the COP of the heat pump must be able to overcome that cost impact. So how do we figure out where recovery of heat has a better return on investment than the use of heat pumps? Because we want to recover heat first if we can, and then when we can't recover the heat, use a heat pump to take the waste heat and move it to a higher temperature. And this becomes a process optimization exercise. And pinch analysis is one of the methods for doing this. So it shows us how much of the hot streams we can exchange with the cold streams, how much of the hot streams is left over and has to go to cooling, and how much is left for heating that is needed to keep the cold stream up. And what you see here is a composite stream for all the streams that have to be cooled, and a composite stream for all the streams that have to be heated, but you see two streams. Now this method can be taken to another level. If you go to the next slide, where we can put both the hot and cold streams together as a combined stream, show all the streams that are cooling down and the heating required for them, and all the streams that are being heated up and the heating requirement for them, and all the streams that are cooling down and the cooling requirement for them. And it becomes a way for us to know how much of a temperature lift we need from waste heat that's available and where we can use it. This particular method allows for establishing initial optimal strategies for heat recovery and application of heat pumps. And it's called a grand composite curve. And I'll show you an example of that when we go forward. In terms of the feasibility, we first have to do a sample process catalog which shows the heat sources and sink temperatures and possible pairings. The next step is to understand the quantity of heat available and when heat is available or needed. Are the sources and sinks pairings within close proximity? That can be another factor. So this is a high-level rating function to compare feasible applications, so the precise value is less important than the relative ranking between candidates. Having identified candidates, process sources, and sinks, the next step is to find the best fit application. Of course, with any selection of mechanical equipment, there will be a best fit machine for the operating envelope required by the application. However, if the application is thermally appropriate, equipment selection is an exercise in optimization rather than feasibility testing. And again, you can see the spark gap is going to be one of the key drivers for deciding where we can apply this feasibly and where we can go, where it's not very feasible. Go to the next slide, please. This shows the pinch analysis curves for a particular site. The green circles show the potential for a heat pump. So we're looking at heat available at lower temperatures and how we could move it up to a higher temperature to use it for heating the cold stream. The heat pump would take the energy rejected at the lower temperature and deliver it at a higher temperature to meet process hot water or steam needs. Now, if we take the same diagram and convert it to a grand composite curve, you can now see, for instance, that we can pick up heat from a chiller evaporator at 80 degrees at the bottom, move it up by a 90-degree lift with a heat pump to provide 58% heating for hot water, or we can move it up with a 125-degree lift to make some low-pressure steam, and that could potentially provide 100% of the heating in this case. So the Grant composite curve can be used to estimate the heat pump lift and the amount of heat that can be delivered through the heat pump based on the waste heat available. And we did this for all 6 sites. And for each of the sites, we looked at steam and hot water heat pumps. And you can see that one of the sites did not have a steam heat pump possibility, but only had a hot water heat pump possibility. Of these sites, if I orient you to the table, the second column shows whether it's a heat pump or a steam heat pump. It shows the temperatures and the lift needed, the COP for the heat pump, the efficiency compared to ideal efficiency for a heat pump, the amount of heating that can be provided, and the amount of waste heat available that was recovered as a percentage, and the energy cost savings. And for each site, you can see there's a spark gap. And if the COP is less than the spark gap, which it happens to be in almost all of these, the energy cost savings is negative, which means that the site would have to pay more for energy for achieving that greenhouse gas reduction. And in the top 4 sites, the increase in cost per unit of heating was from about 6% to 25%. And this takes into account 100% of the demand charges included into the electric charge, assuming that the heat pump demand will also increase the demand charges at the site. In spite of this, there were 2 or 3 sites that showed very strong interest in proceeding further from the top 4 sites that are here, and would be the next best candidates to explore for pilot projects for heat pumps. Looking at this data in slightly different manner, if we look at the COP relationship between heat pump COP and spark gap, on this table, the x-axis is the heat pump COP, the y-axis is the spark gap, and we need the COP to be greater than the spark gap, which is below that blue line, for the operating energy costs to be lower than the existing energy cost with gas. And here you can see that for all the sites, the energy cost savings is not there. And there are some dots closer to the line, so the increase in energy cost wouldn't be as much. But the average cost, if the average cost for electric could be 25 to 30% lower because we can manage the peak demand, you will see in the next graph that all of these red dots would shift down to green dots. And about 4 of them would be in a region where they would generate operating energy savings as well, and would be in a range where if we could incorporate some kind of peak demand management services, peak demand management solutions, or make sure that the heat pump doesn't contribute to the peak demand, there could be energy cost savings for these sites. And that's something that is going to be important for decision makers in terms of implementing industrial heat pumps. So to summarize it, I just want to go to one last slide to talk about the spark gap and pull it all together. So if you look at the data here, this is 2023 in Minnesota. The electric and gas cost is from EIA data from 2023. You can see in terms of electric costs and natural gas costs where Minnesota is on the chart on the left side. If you look at the state rank of the industrial spark gap, Minnesota had the 41st lowest spark gap at 4.62. So the spark gap is fairly high for the state. And so there are some intrinsic challenges to applying industrial process heat pumps. But there are processes where heat pumps can be beneficial. Optimizing the solution and customizing it for sites will be the key to driving that forward. And with that, I'm going to turn it over to John to discuss the market potential in a little more detail.
Yeah, thanks, Chandan. So, my name's John. You remember me from slide 3. Here we are on slide 34. So I'll take you through this next little chunk of the presentation. To create the market potential, we conducted an analysis that extrapolated findings from our particular plants and applied them up to the population level consumption data. So similar to the table that Chandan showed earlier in the presentation, here is MinTap's 2010 survey of total consumption by industrial customers in the state of Minnesota. But this is back in 2010, so we kind of applied a couple of changes to this to get our total consumption that we apply a number of savings fractions to. So first note is this chart doesn't include chemical processing. That was reported separately by MinTap. So that number is actually a little bit larger than the food processing number. You see around 106 million therms in the year 2010. So we'll see that appear on the next slide. But before proceeding to the 3 tiers of potential, we extrapolated the consumption up 25% is approximately the growth of the production in the economy between 2010 and 2025. So that total number comes out to around 400 million therms as opposed to this around 200 million therms when you add that chemical processing back in and then you accelerate up to 2025 production levels. So next slide. This bar chart kind of has the whole story of technical potential in terms of our approach to assuming it. So first, the numbers across the top are the first filter from consumption, total consumption, to the technical potential. And the technical potential is those blue bars, which vary by category and is based on chemical modeling from previous research throughout the country and some of our team's experience. This only considers whether there's heat pump equipment available to produce those gas savings at the temperatures required for the processes. And then you can see that orange bar is substantially smaller. So that's where we lose the biggest chunk of our savings. And that's what we call the economic potential. So the criterion for passing this filter is that the fuel cost before and after is at least cost neutral. And we saw that, without any manipulation of the demand cost in approximately 1 in 6 applications. So conservatively, the assumption here is 15% of the blue bar consumption can be saved economically to create that orange bar. Finally, the third filter is what we call maximum achievable, and it's kind of the realistic case. So this is another filter assuming about 50% of the systems meet this final bar of actual implementation. So that includes more situational or plant side barriers to project implementation. And then on the next slide, I'll roll it all back together. If you add up all those bars to just understanding our 3 scenarios by themselves, it's 32% total industrial consumption can be saved technically or thermally, which comes out to around 12.6 million decatherms. And we had to switch the y-axis scale on everyone to stay confusing. But this is represented in decatherms. And then that 15% filter produces an economic potential savings in orange of about 4.7% of industrial consumption saved by heat pumps. And then that final sort of realistic maximum achievable savings is 2.4%, which is an annual savings of about 1 million decatherms. And for comparison, I think a lot of the people on the call have some familiar with savings forecasts and numbers, but the maximum achievable scenario here would involve an installation of something like 100 to 200 industrial heat pumps. Those largest installations would account for the majority of the savings, but quantitatively, Excel and Centerpoint each forecast about 4 million decatherms for the current triennial. So this maximum achievable realistic scenario is something like one full utility year of savings in Minnesota. And with that, I will pass it on to Shonda to talk about sort of the roadmap to adoption of these systems. Shonda.
Thank you, John. Today I'll walk you through our roadmap for accelerating the adoption of industrial heat pumps in Minnesota, focusing on advancing energy savings, reducing emissions, and helping industrial plants optimize their thermal processes more effectively. Next slide. The industrial sector currently lags behind residential and commercial buildings in adopting heat pumps. While the potential for savings and emissions reduction is clear, uptake has been slow. Minnesota utilities and NGIA pilot projects are beginning to pave the way for broader industrial electrification. We identified 5 key actions in the roadmap for industrial heat pump market adoption. The first 2, market characterization and technology screening, were already covered, so I'll focus on the following: demonstration projects, utility program support, and industry education and promotion. Next slide. Demonstration projects are essential to show successful industrial heat pump implementations that other facilities can confidently replicate. The goal is to coordinate plants, utilities, and funding partners to deliver the first of its kind projects with broad applicability, strong economics, and high heat load replacement. Lower impact, widely applicable systems like those recovering cooling tower loads for hot water are good candidates for utility programs. Higher impact, site-specific systems like thermochemical processing require deeper technical collaboration and customized support. An ideal demonstration site will be open to sharing results and showcase a repeatable, cost-effective framework. 2 Minnesota utilities are currently pursuing industrial heat pump demonstration projects under the Natural Gas Innovation Act, or NGIA. Here's what we know to date. CenterPoint Energy will be conducting an industrial electrification pilot to electrify low to medium heat processes using heat pumps, conduct a technical potential study, and install up to 3 industrial heat pumps with incentives up to $1.5 million per site. This also includes measurement and verification of system performance. Xcel Energy is looking at strategic electrification support to provide analytical support for non-residential customers. Total available funding is $1.1 million based upon projected savings of the project. Next slide, please. So what is the role of utility programs? Utility programs play a pivotal role in reducing economic and operational barriers to industrial heat pump adoption. Programs such as Minnesota's ECO Act, the Efficient Technology Accelerator, and CARD lower resistance to optimization at multiple scales. However, industrial customers often have more complex decision-making and greater inertia than residential or commercial customers. Minnesota utilities currently support industrial electrification and heat recovery primarily through their custom programs. All utilities in this project's advisory group rebate electric heat improvements and are expanding fuel switching options under the ECO Act. As noted in the previous slide, NGIA funding enables targeted studies and pilots to test new electrification pathways. So each of our Minnesota utilities have unique approaches. Xcel Energy focuses on process and commercial efficiency programs and consultant networks. CenterPoint Energy leads the largest NGIA plant in the state. Otter Tail Power demonstrates agility in launching electrification prescriptive rebates. And Minnesota Power continues to use custom programs, noting that cost remains a significant barrier despite growing interest in emissions reductions. So what are the pathways to expand adoption? Rate design and program structure are also critical levers for increasing industrial heat pump adoption. Industrial customers often require bill engineering to close the spark gap, the economic disparity between electric and gas energy costs, as explained earlier. Utilities can address this through demand management products, predictive rate pilots, and price structures indexed to natural gas costs. Additionally, bundling passive energy recovery with heat pump projects and integrating electrification into existing efficiency programs can also improve cost effectiveness. Enhanced customer services such as funding audits, feasibility studies, and design incentives, along with promoting advanced methods like the pinch analysis, will help utilities attract stronger proposal and accelerate market transformation. Next up. Industry education and promotion are critical for connecting skilled professionals, engineers, consultants, and program facilitators with plant managers. This helps plants identify internal opportunities for process optimization and apply technical expertise effectively. Current efforts underway include DOE-funded workshops led by the Industrial Heat Pump Alliance, made up of ACEEE, Renewable Thermal Collaborative, and NEMA. These sessions emphasize peer-to-peer collaboration rather than sales-driven engagement. Neutral facilitators like utility demand-side management engineers guide the discussion to focus on problem solving and not equipment purchasing. However, there's still some key challenges that remain. Will the key decision makers attend and participate in these workshops? And will the content translate awareness into actual project implementation? While these workshops and peer-to-peer models are promising, education alone isn't enough to drive large-scale adoption. That brings us to the next slide, which is deepening industry engagement to turn awareness into tangible projects and long-term adoption. Deepening industry education and promotion means moving beyond technical familiarity to fostering integrated collaboration among plant engineers, design professionals, and capital decision makers. Historical programs like the Compressed Air Challenge show how targeted education can shift industry norms. Applying the same approach to industrial heat pumps encourages facilities to address heat losses before increasing primary heat inputs, ensuring more efficient adoption. Local and regional programs are more effective than broad national campaigns. Embedding energy optimization into existing industry standards such as FDA manufacturing practices could institutionalize data collection and elevate thermal efficiency as a strategic business priority. This multifaceted approach, combining education, collaboration, and standardization, is essential for turning awareness into action across the industrial sector. So next, I'll turn it over to Dave for our conclusions.
Okay, thanks, Shonda. Yeah, I'm just going to wrap things up for us here. If we can go to the next slide. So first key point, industrial heat pumps that can produce hot water to just below water boiling temperatures are available using a variety of refrigerants. Many manufacturers have systems with supply temperatures from 212 to 300 degrees, and supply temperatures above 300 can be produced using a booster steam compressor. About half of the heat loads require too high of a temperature for commercially feasible industrial heat pump units, but large customers are more likely to have optimal applications for heat recovery, while small customers are more likely to have suitable process loads for lower temperature or air source applications. As we've noted in Minnesota, food processing, brewing, pulp and paper processing, chemical processing appear to have the greatest potential for heat pump applications. And then finally, the economics of the difference in electric versus gas costs are the biggest challenge, particularly for Minnesota, which has a fairly high spark gap of 4.62, which is the 41st highest of all the states in the US. So I apologize for Chandan's previous slide where it said lowest, but we're actually the 41st highest, which means that there's other parts of the country with lower spark gaps that are going to have an easier time with the economic potential of implementing industrial heat pumps. Next slide, please. The processes with the best potential will have waste heat and not use outdoor air as the heat source. The applications that need hot water and not steam are also better as far as having better COPs. For our surveys of the 6 sites, we found good opportunities for 4 of the sites, but economics only work well if the applications don't add considerably to the plant's electric demand. We estimate the technical potential gas savings are about 32%, or 12.6 million decatherm for Minnesota, And the economic potential drops down to about 4.7%. And the maximum achievable savings we estimate to be about 2.4% under present conditions. And that maximum achievable scenario would involve the installation of 100 to 200 industrial heat pumps. Finally, we describe the 5 activities to help accelerate market adoption, but one of the most important on the near term will be completing demonstration installations in Minnesota plants. And as Shonda indicated, CenterPoint Energy and Excel Energy have projects approved that will provide multiple installations. So with that, that concludes our presentation, and we appreciate your time today.
Excellent. Wow. Thanks for the great presentation today. That was really just chock full of great content. Attendees, if you have not already done so, please type any questions into the Q&A panel and send them to us. And with that, I will hand it over to Adam Zoet to facilitate Q&A.
Thanks, Lindsay. Yeah, so just looking over the chat, looks like we have one that's come in. So the question is, does the natural gas trend data from 2010 represent current market potential? Considering SIP's and ECO's impacts on electrification or gas usage since that time, I'd be curious to see how the 2020 through 2025 patterns would impact this IHP market potential and adoption. I'm also curious what states have the lowest spark gaps. Are there specific industries or climate trends that make this more visible, aside from utility rates alone?
John, would you like to comment on the adjustments that you made from the 2010 data to current?
Yeah, I'd say we didn't really consider sort of existing efficiency saturation between 2010 and 2025, like the low-hanging fruit per se being picked. I think that these applications are significant enough of an overhaul for a plant level that if somebody say 5 or 10% with stack economizing on a boiler, that's gonna not have a super significant impact on the potential of full scale sort of heat pump integration project. So I think that's my defense against the lack of sort of modeling the sort of efficiency programs between 2010 and present. And there's a second half of that question. I don't know if I can speak to that. Maybe we could repeat it. It was about spark gaps between different states and any sort of large trends climate-wise. I guess Graphit works in a number of states, so maybe they can speak to that.
No, I mean, in terms of the spark gap, when you look at that graph that was presented, a lot of the states are above the 3.5 range. And so while there are a few where it is low, I really don't know which ones those are, so I might have to dig into that. But when you look at it, it really depends on where the natural gas cost is very high. So the electric costs are fairly stable. They do vary some, but the floor level for the electric is about 7 to 8 cents a kWh. But the natural gas cost sometimes can be very low and sometimes can be very high in the $10 to $14 per decatherm. So it's the gas cost that kind of impacts that. If a particular customer has very high gas costs for whatever reason, then the spark gap would be low. And it's hard for me to know which are the states that are there that have that really high gas costs that could drive the results, but I'd have to look a little more in detail on it.
So I'll just relay some information from a ACEEE blog post, and that they say regionally, the Pacific Northwest, the Southeast, and Mid-Atlantic are the regions of the country that have lower spark gaps.
Thank you. So looks like another comment that came in the chat talks about how the Minnesota Pollution Control Agency is currently designing a industrial innovation program where food and beverage manufacturers as well as food waste processors can apply for funding for conducting various assessments such as pinch analysis and funding for adopting efficiency measures, including equipment upgrades and retrofitting. And looks like that person also provided a link in the chat, which is helpful. So yeah, thank you for that helpful information. Another question in the chat was, would you recommend any further engagement between utilities and stakeholders in Minnesota with their European counterparts who might be further along with applications? If so, any thoughts on paths or venues to engage in?
Yeah, I could maybe put Chandan on the spot, and he interacts with plant managers quite a bit. Do you have any suggestions there, Chandan?
And I was going to add, Shannon, maybe because one of our participating sites did have their European partner on a call with
Yeah,
us. I'm not sure if you could share that information.
yeah. There is a lot of drive with industries that have European headquarters where they've got sustainability initiatives that are driving these things. But I think a lot of the thing velocity in Europe also has to do with the spark gap being different, as well as regulations, carbon costs and regulations for greenhouse gases. So I don't know of any organization that I could specifically say would help in that discussion at this point, but I can't answer that directly in terms of how utilities might be able to find stakeholders with the European counterparts. But we deal mostly with the corporate counterparts across different parts.
Great, thank you. What do you think is the single most important takeaway from the results of this study?
I think from a technical perspective, fundamentally, there are some strong drivers why heat pumps should be used instead of utilizing gas. And there are applications for recovery of waste heat in industries that have to be that would be better served by heat pumps if it was done originally. Obviously, when you're doing it at retrofits, it's a little more expensive. But I think any opportunity for where industries are considering boiler replacements or deferred maintenance and things of that nature, there is a pretty good opportunity in the food sector for sure, and maybe even in the pharmaceutical and medical sector, where lower level heating requirements can be met by heat pumps. Takes some creativity, and it also takes some, how do I put it, additional awareness on global optimization within their site. That is the next step. So I think it will happen. It's just a question of time.
Sounds good, thank you. So I don't see any other questions in the chat at this point, so maybe I'll kick it back to you, Lindsay.
Okay, yeah. I do see one more, and we'll make it the last one, and I'll ask it. And then I'll move us forward. So this is the last one I see. During times where investment and production tax credits are expiring, how has return of investment or payment period been impacted when companies are looking at sustainability projects?
The only way I can answer that question is that there are industries that want to be ahead of the curve, and their motivations are quite different. And there are processes where this would have a good return on investment for certain industries. So I think that there's definitely sectors in the industrial where this would apply and have a return on investment. Obviously, it's a smaller one when the challenges are more. But I also think that there's a fundamental mismatch between when gas is applied for heating, when other possibilities are there. And so fundamentally, there are some engineering fundamentals that would drive people in this direction as the awareness grows. And so there are projects with return on investment because heat recovery and reclaim make more sense than using primary fuels in the long term. And it's not about being green, it's just about doing things the right way.
Excellent. Okay. With that, I will go through some final conclusion slides on where to access resources and things. Oh, and also feel free to email the presenters directly. Their email addresses were on that previous slide. Or if you have questions to presenters and you weren't able to capture their email addresses, feel free to reach out to me at the department, Lindsay Anderson, and I can get you connected to the right one. The recording of this webinar and slide set will be available on the department's website through the Conservation Applied Research and Development webpage, which is listed on this slide, along with the final report and any other final deliverables. And this will be posted in the near future. However, likely before then, the slide set will be emailed to all webinar registrants within a week or two of today's webinar. And I can include that MPCA Minnesota Pollution Control Agency Industrial Innovation Program information that was shared in the MPCA specific context for that. When the deliverables from this project are available, you can access and link to those resources from the Research Since 2020 webpage circled in red among the lists of other CARD research projects and available deliverables for projects completed since 2020. Besides research, since 2020, the department's R&D webpage has CARD program resources, such as program background and grantee information, as well as provides web links through the left panel to Commerce's Actions and Regulatory Project Search for final reports or web pages of deliverables for CARD projects completed before 2020. And to keep aware of upcoming CARD webinars as they are scheduled and other news related to Minnesota's Energy Conservation and Optimization Program, do sign up for the ECO updates through the department's Gov delivery. A live web link to subscribe will be provided in the follow-up email, along with live web links of other websites shared today. And the Gov delivery sign up can be accessed on the CARD webpage as well. So thanks again, everybody, for participating today. We appreciate your interest in CARD projects. Registration is open for one more CARD webinar coming up in October. On the 28th, the Cadmus Group will present findings from their comprehensive economic impact analysis and cost-effective analysis of ECO, detailing net impacts on employment, labor force, economic activity, and disposable personal income. Learn how these vital findings will inform ongoing and future ECO planning and development at that day. Otherwise, please do not hesitate to contact me, Lindsay Anderson, or my counterpart, Catherine Fair, if you have any questions or concerns on CARD overall, or need the registration web links for the upcoming webinar. And of course, CARD is one of many energy programs within the Minnesota Department of Commerce Division of Energy Resources. So For more information on other Minnesota energy programs, please do visit Commerce's energy website listed there. And that ends the webinar today. Thank you so much to everybody presenting and attending, and we hope you take care and goodbye.